Hello everyone. Today we have learning about the refraction of the light on from the optical interfaces. This is fundamental of photonics. Actually, this is a material of IGCSE, also as level or A level in physics 9702 or 0625. Before we continuing this video, don't forget to subscribe my YouTube channel. Don't forget to like, comment, or share to this channel. Okay, we directly discuss about the refraction of light from optical interfaces. I will close my face first. Yes, this is refraction of light from optical interfaces. When light is incident in interface, the geometrical plane that separate one optical medium from another, it will be partly reflected and partly transmitted. We can see here, partly as reflected and partly as the refracted. In figure 3.7, so a three-dimensional view of light incident of partially reflecting surface or interface being reflected there according to the law of reflection and reflected into the second medium. The bending of light ray at interface between two optical media is called refraction. Yeah. The bending of light rays at an interface between two optical media, is called refraction. Okay. Before explaining the detail of process of refraction, we need to describe optical media in terms of an index of refraction. Okay, we can see this one. This is the uh, interface between two medium, the medium below and the medium on the up. Let's say this is the three dimension of ray path. When we have incident ray, on the left side, this is incident ray on the left side, and this is partly on reflected ray and also refracted ray. Yes, this is plane contains normal incident reflected and reflected rays that angle of A equals to angle of B. Angle A equals to of MG. This is actually about the law of reflection. You can see this is reflection and refraction as interface. This is interface. Okay, we continue again. Now about the index of refraction. Index of refraction. Let me read first. The two transparent optical media that form an interface are distinguished from one another by constant called as the index of refraction, generally labeled with the symbol m. The index of refraction for any transparent optical medium is defined as the ratio of the speed of light. I repeat again, is defined as the ratio of the speed light in a vacuum to the speed of light in the medium. Yes, I repeat again, the index refraction for any transparent optical medium defined as the ratio of speed light in a vacuum to the speed light of in the medium is given in the equation 3.1. So I can block this one here. Okay, now we have the formula of n small. N is index of refraction of the medium equals to C divided by V. C, speed of light in free space vacuum. This is actually about constant number. And V, speed of light in the medium. V is speed of light in the medium. and back again n index phase of refraction of the medium. So the index of refraction for free space is exactly 1. For air or most gases is very nearly 1, so is most calculation. It taken by to be 1.0. From other material it has values greater than 1. Table 3.1 lists index of refraction for common materials. We have table this one. You can see this one. This is some materials and has index refraction, yeah, at the in the nanometer. For the material at 598 nanometer, this air is 1.0003, yes, and benzene also 1.50, carbon disulfide 1.63, and we have glass for flint is 1.66, and so on and so on. Okay, this is the constant number, or this is the index of refraction for forest material at 589 nanometer. Okay, so the greater the index of refraction of medium, the lower is speed light to medium, and the more light beam is going from into the medium. Figure 3.38 so the general cases one light passing from the medium of lower index to higher index to other from medium index to lower index. Okay, we can see this one. Yes, I repeat again. Figure 3.138 so the general case of the light passing from the medium of lower index from lower index, yeah, to the higher index, and the other from higher index, yeah, and to the lower index. Note that the first case, lower to higher, the light ray bent toward the normal. Yes, you can see this one of the refraction ray. This is toward to the normal. And in the second case, higher to lower, the light ray is bent away from the normal. This bending is away from the normal. Yes, it is helpful to memorize this effect since they often help one trace light through optical media is a generally correct manner. Okay, you can see again, this is the case 1 is lower to higher, bending toward normal, and the case 2 is higher to lower, bending away from the normal. So, now about the Snell's law. Snell's law of refraction relates the signs of the angle of incidence of refraction at the interface between two optical media to the indexes of refraction of the two media. The law is named after Dutch astronomer Wilbert Snell, who formulated the law in the 7th century. Snell's law enables us to calculate the direction of refracted ray if we know the refractive indexes of the two media and the direction of the incident ray. The mathematical expression Snell's law and accompanying drawing given figure 3.9 here. This is about the Snell's law. Yeah. Ratio between sin I divided by sin r equals to index r and divided by index I. This is interface, and this is medium 1 and this is medium 2. Medium 1, depending by medium 2 is higher than medium 1. This is incident ray. So, because n are higher than ni, the refracted ray will be going near with the normal. I is the angle incident, R is the angle of the refraction here, and NR is index of incident medium, and R is index in the refracting medium. Note, note carefully that both angle incident I and refraction R are measured with respect to the surface normal. Note also that the incident ray, normal, and refracted ray are lie in the same geometrical plane. In the practice, Snell's law is often written simple as the Ni sin I equals to Nr sin R. Now let's look at example that make use the Snell's law. We have example. In a handled optical instrument used underwater, light is incident from water onto the plane surface, the flint glass, at the angle is incident of 45 degree. Question I. What is the angle of reflection of the light of the flint glass? B. Does the refracted ray bend toward or away from the normal? C. What is the angle of refraction in the flint glass? So the solution is, from the law of reflection, the reflected light must head of the angle 45 with the normal. Note the angle of reflection is not dependent on the refractive index of the two media. Solution B. From the table 3.1, the index refraction is 1.33 for the water and 1.63 for the flint glass. Thus light is moving from lower to a higher index refraction, it will be toward in the normal. We know then angle of refraction R should be 45 degree. Okay. Now about the question C. From the Snell's law, equation 3.2, we have an I sin I equals an R sin R. When Ni 1.33 and I is 45 degree and N1 1.63, we can say that sin R equals to 1.33 sin 45 divided by 1.63, and we get number 1.577. This is actually sin R. And so R equals to sin minus 1 of 0.577, we get 35.2 degree, or the angle of refraction is about 35 degree less than 45, just was predicted part B. Note the function sin minus 1 is the course of the arc sin. Yeah, we will use the sin minus 1 notation since that is what is the form of the scientific calculators. Okay, now about critical angle. Yeah. When light, yeah, this is the critical angle and total internal reflection. When light travels from the medium of the higher index to one of lower index, we encounter some interesting result. Yeah. Revert to figure 310, where we see four rays of the line originating from point O in the higher index medium, each the incident of the interface. At the difference angle incident ray, ray 1 is incident interface at the 9 degree as the normal incidence, thus there is no bending. We can say ray 1, when the incident ray coming from the Ni, when Ni bigger than Nr, so this is the trace one. The light when the incident ray as the normal incident 9 degree, so we can say this draw 9 degree also on the refracted, and this is the right two. The right two on the angle something I and then R is away from normal, and actually 3 when the I critical angle, yeah, critical angle and R on the 90 degree, and on the fourth ray, this is total internal reflection. Yes, as we call it, this is as the inter I is critical angle. Okay. The light is direction implies speed of the second medium y, but continues along the same direction. Right 2 is incident I refract back away from the normal, at the angle r. Right 3 is incident at the critical angle IC large enough to cause the refracted ray bending away from the normal arm to bend by 90 degree, thereby traveling along the interface between the media. This ray is trapped in the interface. Ray 4 is incident on the interface at the angle greater than the critical angle and totally reflected into the same medium from which it came. Ray 4 obeys the law of refraction, so that its angle of reflection is exactly equal to its angle of incidence. We exploit the phenomenon total internal reflection when designing light propagation in fiber by trapping the light in the fiber through successive internal reflection along the fiber. We do this also when designing retroreflecting prism, combined with ordinary reflection from mirror. The sharpness and the highness of totally internal reflected light beam enhanced considerably. The calculation of critical angle of incident ray of the two optical media whenever light is incident from the medium of higher index is a compliance with Snell's law, referring to ray 3 in figure 310. Using Snell's law in the equation 32 appropriately, we have N1 sin IC equals to NR sin 90 degree. Yes, where N is the index for the incident medium, IC is the critical angle of the medium, NR in the index for medium, the lower index, NR equals to 90 degree is the angle of refraction of the critical angle. Then since 90 equals to 1, we obtain for the critical angle. Okay. Finally, we get the sum equation that IC since minus 1 of NR divided by NI. Let us the results now so to determine the entrance cone from the light ray incident of the phase of the clad fiber in the light of the trapped by total internal reflection at the core cladding interface in the fiber. Example 3. A step fiber 0.005 inch in diameter has core index 1.52 and cladding index of 1.39. See drawing. Such clad fiber use frequency application involving communication, sensing, and imaging. We can see here this is air with the index refraction of air is 1.0. This is actually incident angle, and this is the refraction angle. So we get theta critical equals to here when refracted angle as the 90 degree. This is cladding with index refraction 1.39 and fiber core and 1.53. What is maximum acceptance angle theta m for the cone of the light ray incident of the fiber phase such that the refracted ray in the core of the fiber is incident on the cladding at the critical angle? The solution is first finding the critical angle theta c in the core at the core cladding interface. Then from geometry, identify theta r and use Snell's law to find theta m. For equation 3.3, at the core cladding interface, we have theta c sine minus 1 index refraction of the cladding end and divided by index refraction of the fiber core. Finally, we get 65.3 degree. And 2. For the right triangle, theta r equals to 90 minus 65.3, so equals to 24.7 degree. Then, for the Snell's law on the fiber face, we have index r sine theta m equals to index core sine theta r. So sine theta m equals to n core divided by n r sine theta r. N core is 1.53 and n r equals to 1.0 and times sin 24.7 degree. We get sin theta m equals to 0.639 and theta m we get sin minus 1 of 0.639 equals to 39.7. Okay. Thus, the maximum acceptance angle of 39.7 and acceptance cone which are 2 theta m 39.7 degree. The acceptance cone indicate any light ray incident of the fiber face within the acceptance angle will undergo total internal refraction of the core cladding face and remain trapped in the fiber as it propagates along the fiber. Okay, thank you very much for watching my screen video. Don't forget to subscribe my YouTube channel. Please comment if any you need to ask me about this video or something else. Like and share to the other. Thank you very much. Bye on either video.